Thanks for joining, everyone. Today, I am happy to be joined by Michael Hawkshaw and James Eggleston from the European Space Agency. Both they are going to take us into a journey into space and into the IT infrastructure that help them support space missions that can span several decades. Michael has more than 20 years of experience in the industry. He started in the software development space to move to the project management space, and today is of operation infrastructure IT service manager. James has more than 25 years of experience supporting and developing ground stations that can support several space missions at once. He's software solution manager. Welcome both, and the floor is yours.
Michael and myself will present on how ESOC is modernizing our data and IT infrastructure to help support us with space exploration using AI. So, the outline of the talk will be roughly 3 segments. First, I'll talk a little bit about the background of the European Space Agency, ESA, and deep dive a little bit on what the operations center here does. Then Michael will bring the IT infrastructure of the future, what we're planning at ESOC and how we plan to meet the challenges we currently have. And I'll be back at the end to talk about how we support operations and try to gain some insights into what's going on in space and on ground with AI. First, a little bit about ESA. I mean, it is an intergovernmental organization. It's established in 1975. We have 23 members now, and some cooperating states and agreements with, for instance, the EU and Canada. We're not an EU institution, but it's mainly European, but with Canada as an extra partner. The point of ESA is really peaceful exploration and use of space for the benefit of the inhabitants of our member state countries. We want to make space work for everybody, available to everyone. We build rockets, we launch rockets from Guyana, French Guyana, which carry satellites with unique capabilities, and which are designed and built in Europe, in our member states, which perform exploration of the solar system, and Earth and the universe. We also have astronauts and a manned space program as well. The main aim of one of the main aims besides the space is to support technology development, to respond to we build technologies that can meet the unique mission demands, and our engineers work out how to make these systems work at incredible distances in incredibly harsh conditions. And then the technological innovations flow down to the industries on ground for future space missions and also for non-space, right? And of course, ESA is heavily involved on an international level as well with NASA collaboration with NASA and other international agencies. A little bit deeper on the European Space Operations Center. This is where missions come alive, is our tagline. Once a launcher has done its job and the new satellite comes off the top of the rocket in low Earth orbit, that's when we take control of things, and our flight control teams start communicating with the satellite to make sure it's in a fit state. And that continues then for the entire lifetime of the satellite, which can be up to 20 years, as I'll come back to later on. So ESOC is a center of excellence for space operations, for satellite operations. We have the engineering teams that do build the systems, but also operate and do space safety. So, for instance, in ground systems engineering, we have experts in flight dynamics, ground stations, so, radio frequency and optical communication, in mission data systems that we use for storing all the data that we receive from the spacecraft and sending commands and planning and simulating and preparing the missions, and navigation systems that are used by various missions. Each discipline typically has a common core software that is then developed over many years, meeting the needs of all of the missions at ESOC, and we reuse these packages and redeploy them for each mission. So we do have a problem or a drive that we need to make these systems long-lived. Again, usually multiple decades. space safety, they focus on dealing with threats to the Earth or to society, so near-Earth objects, perhaps an asteroid or comet, but also space debris and space weather, because any significant disruption to space will have a very large impact on society. We rely on satellites for communication, for navigation, timing. It would be there could be significant negative effects if we don't manage, if we're not aware of what's about to happen. These systems are developed and handed over to our mission operations experts, who would usually spend several years learning every inch of a satellite and how it works. Each one is typically unique, and we then use the ground systems to fly and control the satellites to make sure that their investment is maximized, because some of these satellites do cost a lot of money, hundreds of millions of euros, and we want to maximize everything that we can get out. A little flavor of we have three main branches, if you want, or three main families. Interplanetary satellites, so that's satellites that leave Earth orbit and go to other planets in the solar system, or other locations in the solar system. And typically these missions are very long-lived. They usually have a very long cruise phase to reach the destination. So for instance, we launched JUICE last year, and it will arrive in 2031 and then begin its operation. So you can imagine that our systems of communicating with JUICE right now is the system that we'll have to carry on using until that end of life, most likely. Astronomy satellites is the second leg, the second part of the family. This is typically taking pictures in various parts of the electromagnetic spectrum. And again, some very long-lived missions. We have one that was even launched in 1999. This gives us challenges because we need to. Sorry, my slide thing. Yeah. This gives us some challenges because we do need to make sure that these satellites remain in a good health for the full duration of the mission. This slide is the last leg, the observation satellites. There are three parts. We have science missions, typically flying new payloads, first of a kind for the first time. We support EUMETSAT, which is the European meteorological agency, in some of their activities, and also Copernicus is an EU program, and EU and the ESA are working closely together to prepare and launch satellites. And I think the main point on the slide here is to see that as the clock ticks round from 2010 to 2030, the number of satellites that we're flying is going up significantly. So whereas maybe 20 or 30 years ago, ESA could launch a satellite maybe once every 2 years, now we're launching satellites every few months. And by the end of the decade, instead of, we'll have around about 40 satellites, 45 satellites in orbit, if plans are all followed. So this is a huge increase from what we have now, which is only 25 satellites. And this constant challenge to become more efficient and enable the T's here to be able to deal with this workload is one of the things that I'll come back to when we start talking about the AI. But it is as challenging as it all is. It is all worth it, because when the next slide loads, you'll see some fantastic images of stuff that we're trying to protect and monitor. Looking for solar flares. We've measured the true shape of the Earth, for instance, there, pictures of the universe. And new missions coming up that challenges even further. For instance, Mars sample, which we're going to send a satellite to Mars. We're going to pick up a sample from the surface, which has been created by one of the NASA rovers, and fly that back to Earth for investigation. So I hope that gives you a flavor of the sort of things that ESOC is doing and controlling. And with that, I'll hand over to Michael, and he will talk a little bit more about the IT side. Michael.
Thank you very much, James, for that introduction and that overview of ESA. I'd like to spend a few minutes just to describe to you our journey of our IT infrastructure, which we have for our mission operations. So starting with the past and what we are doing right now. On the next slide, we will talk about the current legacy missions, if you like. And while I say legacy missions, as James mentioned, we had one satellite launched in 1999. That was XMM Newton, still flying now. Managed to find creative ways to extend the life of the mission. It's all pretty much automated in terms of its operations. And because of that, the cost is low of running it, and it's still giving us good science data, so we keep it running. So while we say legacy missions, some of them are actually 25 years later still being operated. In terms of the IT infrastructure, historically we had, as James also mentioned, fewer, less complex missions. Some of the spacecraft, like actually this 25-year-old spacecraft, had no onboard storage. It wasn't a thing at the time. So we always had to maintain contact with that spacecraft. If we didn't have that contact, we would lose that data altogether. And really, ESOC was only focused on controlling these satellites and spacecraft that we were operating. So back then, each mission would have its own dedicated service, its own dedicated infrastructure. The mission control system, which is one large piece of software, along with lots of other auxiliary applications, they'd all be installed directly onto that operating system running on that server. Very little was shared between missions. It was all required for that mission and run by the mission as its own little operation. But as the number of missions and their complexity notably increased, this started to become less efficient and less cost effective. And at the time, of course, new technologies were starting to become available, which we could start to look at, evaluate, and see if we could use these in order to help do more with less. Also to point out here that unlike, for example, a global network of internet satellites running in low Earth orbit, where you have a large number of identical spacecraft, which makes the operations very easy to operate, ESA tends to have a large number of one-off bespoke science missions. So this spacecraft or this satellite, depending on the mission, has never been done before. So this can make some of these making this a generic approach or automating some of these aspects a bit more challenging. So obviously we couldn't stay with this dedicated solution. We went out of space for one thing with the number of missions that we were coming on board. This was far too costly to maintain this approach. So we started to embrace then virtualization. And on the next slide, we'll show that we have some large virtualization servers and vBlock, which we could then start moving our workloads onto these instead. It's still the same kind of concept ultimately, but instead of running your mission control system software in an operating system on the physical server, it's now running a virtual machine. So it's more of a move to this. It did mean though that we could have more efficient use of our resources. Took up a lot less space. Not all of these machines are all running 100% of the time. They're not all maxed out. There are times when there's quiet periods. For example, for the deep space missions, you might have a pass every 24 hours, and then you have 24 hours worth of data to process all in one go. And the rest of the time, it could be there's not much happening. So this meant that we could over-allocate the resources accordingly and be able to accommodate more. We also started to have more shared storage options, so shared file systems available. And we also had our first truly shared infrastructure with our long-term archive. So we developed a way of we wanted to be able to archive all of the telemetry, and the telemetry is the information about the health of the spacecraft, and the telecommands, which is what some of the commands which are sent to the spacecraft. Wanted to be able to have a way of being able to archive this for the history of these missions altogether. And if each mission did its own thing, we just wouldn't be able to accommodate that. It would be too costly and there'd be no space. So we had our first shared infrastructure based on Hadoop, HDFS, HBase, where we could then just scale it up by adding additional servers to add to the compute and the storage capabilities to be able to accommodate all of that data for these missions. The science data, though, which is far greater, is not handled by ESOC. It is handled at other locations. So that was our move to virtualization. But of course, our journey doesn't end here. ESOC is also home now to the Space Safety Program. Wasn't before. This brings in new use cases for IS infrastructure, along with IAI projects, which James will talk about shortly. And we needed a way of being able to manage this different profile of resource usage and be able to more efficiently use our infrastructure. Because no servers are very expensive. You want to be able to make sure that you're maximizing the use of them in order to maximize your return on your investment. So to be able to cope with these greater number of missions, the software side changed. We started to embrace more automation. The applications were containerized, split up into more microservices-based architectures to be able to scale more easily. And this, of course, required a suitable container orchestration system. This will also allow us to maximize the resource utilization. We could have workloads which were not so critical running when missions, for example, are not processing that data from the last pass. So we could always make sure we're using these resources accordingly. For storage in particular, we also needed a solution to consolidate the various solutions that we had to be able to offer like a one-stop shop for storage. And for us, it was very critical to be able to scale this out instead of up. This means that we could, in theory, scale that out infinitely, adding additional infrastructure nodes rather than being restricted to a physical limit that we could have. And we wanted to be able to do this using standard servers and standard storage. So I think it bespoke or custom. Of course, we'll also want to support open source, adopt industry standards, and support the European industry. So with that was also a driver in the technologies that were chosen. Also, this technology is also quite complex to run. So in order to help us to focus more on our core business, what we do here, we started to move more towards managed services. So we'd have external partners coming to manage these solutions for us 24/7 to be able to step in and help us out when we need that help, particularly during the initial what we call LEOP phase, when we're in low Earth orbit. The initial phase of the start of the mission, that's critical that everything is working well, and we need that 24/7 support to be able to make sure that everything runs smoothly. So in the end, we settled on Kubernetes for container orchestration, Ceph for storage, storage services to offer our block, object, and file system storage. We use databases heavily, settled there for Postgres to support our databases, and Apache Kafka for event store and event and stream processing. On the Kubernetes platform that we have there will allow us to add additional services on top for MLOps, which James will talk about shortly, so we can support these AI workloads. And theoretically, we could also then move this workloads also to the public cloud if we need to. And indeed, we are already doing this. I think by the end of this year, we will have at least one mission running in the public cloud, so that we can reduce the amount of space that we need here. So it's more, again, doing more with less. And but this is our journey so far in terms of our on-premises infrastructure. I'd like to hand over to James now, who would like to elaborate more on the AI projects. Thank you very much.
Yes, thank you, Michael. So yeah, I'll just now do a little bit of a briefing on how we're going about our planning and how we are actually supporting operations and gaining insights with AI. I mean, maybe the first question and most fundamental is why do we have to do this? We're faced with, as has been said a few times now, ever more missions. They're getting more complex. They have more data. They're more varied as the numbers grow. So we need, unfortunately, we don't scale with the same numbers with the workforce and with the funding. So we have to get more efficient and be able to do, like I say, more with the same or even with less. So there's four main themes where AI can really help us. One is improving our operational efficiency. We are asked to do more. We have more simultaneous demands, so we have less time. And the AI helps us augment the human capabilities. It's not about replacing the humans. It's really about helping them maintain quality and give them an easier life. Yeah? Also, AI has a role in how we make decisions. Traditionally, it's something is happening. We gather all the data, we access it. AI can obviously process all the data all the time, being not based on humans. And we can, for instance, use digital twin technology to run multiple scenarios and explore answers to potential issues that's going on board. Proactive maintenance is the third sort of aspect. A stitch in time saves 9. And if we can detect something happening maybe days or weeks before it causes a problem, then obviously we can avoid surprises, we can avoid downtime. Not everything can be prevented, of course, but if we can, then this is a huge benefit for efficient operation. And the final point really is using the AI to help us improve the depth and the breadth and the depth of the analysis that can be performed. For instance, you can monitor more parameters more closely, more often, rather than just perhaps maybe once a week reviewing the status of the spacecraft. To sort of assess where we would go as a management, we launched a sort of an assessment, system-wide or business-wide assessment. We narrowed down 40 use cases based on the impact of the AI, the feasibility, and also the commonality of the data being processed. And this week generated a business plan or a business case. AI as we're now implementing that plan. There's two sort of side effects, which is sort of in line with the ESA purpose. One is that we help define new value propositions. So ESA doesn't directly, our staff don't directly code the solutions ourselves. We play a more technical oversight role. Industry comes in, they make proposals, and we work with industry to develop these solutions. So industry end up getting experience and developing solutions that they can then reuse and resell to other players. This generates a sort of a value chain this generates a value chain for the industry who take part work with us. There's a side effect which is we found is that the need this AI demands need to have a solid data foundation, and this is something I'll delve into in a little bit later on. But the side effect is it creates an ecosystem for this data for industry, academia, scientists, engineers who want to explore how systems behave in space. Some main achievements of what we've managed to get already. We have an AI assistant which we built, which does correlation and retrieval of information from the multiple data sources that we have. Typically, each system has its own data source. So correlating all of this data, building a knowledge graph and using natural language processing techniques. And we're also now working on large language model techniques, helps the operators find information much more efficiently and ask sensible questions. We have an MLOps platform. If we want to use AI, we need to train the AI, and the AI will need retraining, and we need to monitor the accuracy of the results. This is something which is a MLOps concept. So we have a platform which we developed based on open source standards or open source practices, the best of breed tools to allow us to centralize and coordinate the AI scale of ESOC. Maybe as a more concrete AI use case, we have an optimized mission planning solution. It's actually potentially more to do with automation than AI, but it demonstrates the concept. We've managed to make a very routine and mundane and repetitive task, completely automate that in the large majority of cases, such that people are saving a significant amount of time. It's in the sort of 20% margin on that particular task. So for several months per year, it's being saved. And it allows these extremely talented people to then work on other aspects, perhaps more noble challenges than a routine activity. There's also tools for satellite health forecasting and root cause investigation. And these are being developed further by further activities to make them more efficient so they can be deployed operationally. I have to say, generally, when we did our business case, we made assessments of the expected return on investment. And actually, when we've actually now measured it and developed a tool, we are seeing statistically twice as much as we sort of conservatively estimated. So there is a real value there in developing these solutions as well. A little bit on the more technical side of things. As I said on the previous slide, we have a number of data sources. There's a sample there on the left hand of the slide. I think the key point to note is each of these systems was developed at some point in the last decades. They all have their dedicated internal data stores. It could be a database, it could be a file store, whatever. And we need to get the AI to work. It needs access to that. And getting that data out processing it is a huge challenge in the current architecture. So we've got to put in this abstracted data access layer where we build a data foundation, as we called it, with an architecture and a governance, proper data management. And of course, that then allows the AI solutions to be plugged in on top to do that processing and to deliver the value to the end users. This is a key step for us, provides glue to avoid that every solution has to talk to every data source. This is obviously going to scale for us. And finally, a little bit about our enabler platform. It's a basis for our operational AI. I think Michael already said on the previous slide, we do need to sort of avoid vendor lock-in and avoid solution that is somehow can survive for many years, potentially decades. So we've gone with an approach where we've taken, let's say, standard tools from the AI and the MLOps community, Ubuntu, these, for instance, and others, and we've configured those to work together on top of Kubernetes to provide a kind of a platform as a service for ourselves. And the AI solutions sit on top of that, and so they're not dependent and not talking directly to the ground systems where the data is. Ultimately, the aim is that we avoid that every AI solution is its own unique stack, because that would be extremely inefficient for us, both in the terms of IT and then operations, software maintenance and then operations costs. So that is a very brief and probably not deep enough description of how we're working and what we're trying to do. I'll conclude now. We are embracing new solutions and technologies. That's our role, to find new ways of exploring space, challenge the traditional approaches and do things in different ways, de-risk some new technologies and techniques for our unique space missions, and ultimately to support the industry of our member states to help them in their commercial activities. Michael's described how the on-premise cloud is allowing us to be much more flexible and efficient in the way we manage our missions, giving us auto-scaling of workloads and much better resource usage and resilience against failures. And then finally, I described how our AI solutions and MLOps plans are helping us deal with this increasing complexity and size and data of all of our current and planned space missions that we're going to have to fly here at ESOC, because the AI solutions AI solutions allow better solutions to the existing functionality. It allows new solutions, things we can't do today, and alternative or improved concepts for approaching the way we approach mission operations. So with that, that's the final slide. I'll say thank you for your interest, for your attention, and things back.
Thank you for the insights that you did share with us around your IT modernization efforts, around your IT stack, and around how you are intending to support the space mission for several decades to come. That was very interesting. If you agree, I would like to ask you a few questions to benefit from your presence here with us. The first question is basically, what are the use cases that you are going to enable with Canonical Solutions?
Sure, on the IT infrastructure side, we contracted Canonical to help support us with our broadly managed services for our Kubernetes services, which is for managing our missions, the upcoming missions, also for the Zephyr infrastructure, and to come as well, Postgres. So our mission control system is already using Postgres, but we'd like to be able to have a way of having it managed for us, hosted, replicated, so we don't have to worry about how it's going to work. Yes, and on the AI side, James, have a few words.
Yeah, the main case for looking at the moment is the use of charmed kubeflow for the basis of the AI MLOps platform, and that's one of the main. And some of the other charm packages might come into question as well. As you saw, we're using open source packages. Typical, we do need to support these packages, and if we do it ourselves, it's obviously inefficient, and getting best of breed industry support is obviously quite attractive for us.
Okay, thank you again for, let's say, the insights, for your time today, and for the answers provided. That was really very insightful and inspiring. Thanks again, and have a good day, everyone.